Welcome, everyone. At the end of the talk, there will be a Q&A session. So if you would like to ask a question, please raise your hand and enjoy the talk.
Thanks. Hey, everyone, and thank you for attending this talk. So before we jump into it, a few words about ourselves for those who don't know us yet. So I'm Johan Mabille. I'm a technical director at QuantStack and been working on the Jupyter project for 7 years now, and I'm now a member of the core dev teams. I mostly work on the backend side, so I co-author the Zeus stack that we will talk about in this talk, and also develop the backend for the debugger in the Jupyter ecosystem. And in parallel of that, at QuantStack, I'm leading the development as a Mamba team. And Thorsten here with me is a scientific software developer at QuantStack. I think you joined us like last year?
2 years ago.
2 years ago. Oh, really long. And co-authored the mscript and Forge stack, so that we will demonstrate in this talk. And he also contributes to many other open source projects, including Extensor, which is another one that we develop at QuantStack. So a few reminders of the Jupyter global architecture. So Jupyter has been designed around the Jupyter Kernel protocol, so which is a well-specified protocol built upon web standards, and it's used like it enables like clients, for many clients, Notebook, JupyterLab, but also Spider or Qt Console or whatever, to speak with lots of different kernels. So currently there are more than 100 kernels, and so supporting 40 different languages. Without diving into the whole protocol, so just a few things to remember. So client kernels communicate over the network through 5 channels. So the shell is responsible for the code execution, for code completion, and this kind of thing. The control channel is responsible for starting, asking the kernel state, asking info, sending debug requests when the kernel supports a debugging protocol. stdin is for input. IOPub is a channel where results are published. So if you have many clients connecting to the same kernel and you execute some code printing something, every client will see the output. And the outbit is like a technical channel just used to maintain the connection and be sure that the kernel has not died. So this is something really common in middleware. And all the communication and the message are sent through this channel, so over the network, I said that, and it relies on 0MQ, so which is a middleware library, which provides a low-level transport layer. So now that we have this protocol, let's say you want to write a kernel for Jupyter. So you have 3 different approaches. The first one is writing a kernel from scratch. So that's the approach of iJulia or IR kernel, for instance. Also IPyKernel. Another approach is to use what we call the kernel wrapper approach. So you can reuse the machinery from IPyKernel to develop your kernel. This is easy to set up. These are some drawbacks, especially, so the first one is you depend on Python runtime. The second one is you have to redirect output and input from Python, and this might be unstable. The third approach is to rely on something we developed at QuantStack called Zeus. So it's a native implementation of the Jupyter protocol. The nice thing with Zeus is it's C++. So if your interpreter provides a C or C++ API, it's really easy to write some glue code between Zeus and the interpreter, and you don't have to worry about implementing the protocol. So yeah, it simplifies the implementation of kernels. Your developers can focus only on the implementing the interpreter part, or if you already have an interpreter, just like writing some glue code. We have a tutorial for how to creating a kernel based on Zeus in the Zeus documentation, so just like step by step what you have to do. And also for more advanced users or developers, Zeus is architected around 4 main components that we will see later, and that you can just like replace with ad hoc implementation. So it's really easy to extend it. So we have like a lot of kernels. I won't dive into all of them, but maybe like 15 kernels, I think. And one of the most important components is the Zeus cookie cutter. So this will just like create a repo with everything you need to build, so the CMake, the CI, everything, the documentation, skeleton. So you just like focus on writing your interpreter and the specific things to your kernel. So to implement a kernel, here is an example. So you have to start with the cookie cutter, and then you have to implement some methods, just Actually, if you look at the snippet on the right, so what you really have to do is to inherit from this base class and just implement like 5 or 6 methods. So it's really, really simple and really straightforward to do. So once you have your kernel, so the way it works and traditional workflow in Jupyter until now is you have your kernel. Your kernel is talking to some client. So if you have a web app, the client will be the Jupyter server, and they're communicating through this ZMQ with this ZMQ library. And then you have the front end. You have also some clients that directly talk to the kernel, so you don't have any server, like the console, for instance, or the Qt console. So in this case, they also use the ZMQ library to communicate with it, and you just don't have any server. So it can be a bit confusing, but yes, what you have to keep in mind is all these clients required some deployment and infrastructure. So if you want to scale to hundreds or thousands of users, it's fine, it works. Now, if you want to scale to a nation, for instance, to millions of people, this requires a huge infrastructure, and it's super cumbersome to maintain. So that's where we need something different. And that's where New Beast come into play. And I let it to Thorsten to present WebAssembly.
Hi, I'm Thorsten. So probably you have heard about WebAssembly. So WebAssembly is this awesome technology. So it's a binary instruction format for a stack-based virtual machine. But at the end of the day, it just allows you to run compiled C or C++ code in your browser. So it's really portable. So it means typically it runs on any browser. So you don't have to care which OS the people are using. And yeah, it's to deploy compiled code to the web. So Emscripten is a nice compiler using LLVM, which essentially gives you the WebAssembly. So you don't have to learn a new language, WebAssembly. You just take your existing languages like C, C++, Rust, throw Emscripten at it, compile the stuff, and then it spits out WebAssembly, which you can then use. Typically, it's not as fast as native code, but not slow. So it's maybe 2 times slower than the native code, so still fast enough. And you can build awesome things with them or compile awesome things. Of course, you can run Doom in the browser. Or even more spectacular, there is a x86 emulator. So if you have not seen this, you should go to this website. So they have a complete emulator written and compiled with WebAssembly where you can load Windows 2000 or whatever in a few seconds. And it's really awesome technology to play around, but probably not so useful for doing any science. So, but for that, there are cool things like Python compiled to WebAssembly. So this is called Pyodite. So this is a complete Python distribution compiled to WebAssembly. So what does this mean? It's not only the Python interpreter, but all the packages we love, like NumPy, Pandas, and so on. And it runs in the browser. So what can we do with this? Well, obviously, we can write Wasm kernels. Since we have now Python in the browser, we should be able to also write kernels for Jupyter, which run in the browser. Recently, also Erlang has been compiled to WebAssembly. And it's essentially the same, so it runs in the browser. A few packages are also compiled to WebAssembly. There are not that many packages yet compiled to WebAssembly for R than for Python, but it's going there. And you can also write Wasm kernels for that. So which brings me to JupyterLite. So probably you have heard about this yesterday from Jeremy. So, but I recap a bit what JupyterLite is. So first, you can find it on GitHub, of course. And JupyterLite is a JupyterLite distribution that runs entirely in the browser. What does this mean? Well, the code you execute in JupyterLite is not running on some server somewhere. It's literally running on your machine in your browser. So no data is sent to any server whatsoever. It's on your machine. So, but to do this, you of course need also the kernels to be compiled to WebAssembly, because without kernels, JupyterLab cannot do that much. So, as I said, there was a talk yesterday. Feel free to check the slides out, where you can learn a bit more about JupyterLite. So, since JupyterLite runs in the browser, we can easily embed it in an iframe. So here, this is not actually a screenshot. This is like the actual thing. So let's see if we can use it right away. So there's one tiny downside. There are loading times, but this time it was fast because I preloaded most of the stuff. And now some live coding. Let's see if this works. Yay! So this works. There are more cool kernels. For instance, there's also a SQLite kernel where you can run SQL commands. I'm not that good in SQL, so I'm just clicking through the stuff here. But essentially, you see the point. So you can query the database and so on. Yeah. So now, how can we utilize Xeus such that the kernels from Xeus are used in JupyterLite? I'm getting a call. So Xeus in the browser, we call that JupyterLite. And let's first discuss a bit the old architecture of Xeus. So here's again the GitHub of Xeus. So Xeus is really customizable. So of course, you can write your own interpreter. That's the main customization people will look at when they want to write their kernel. But there is more. There's a custom debugger. So if your language should have, or kernel should have debugging capabilities, you can write your own debugger for that. And last but not least, there is the custom server. So the server in Xeus handles the concurrency model and how the data is essentially sent to the other components. So even though this is quite configurable, since the Jupyter protocol is basically specifying that we use 0MQ, we kind of hard-coded the use of 0MQ in Xeus, which sounds like a good idea. The problem is 0MQ is not available when you compile for Wasm, because Wasm is WebAssembly is a sandbox, so it gives you strong security guarantees. And therefore, it does not allow sockets and all that cool stuff. So we have to do something else. So what we did now is we tried to make, or we did make Xeus agnostic of the communication layer. So so far, the communication was exclusively done with 0MQ, and we extracted that and created first a dedicated server just for 0MQ. So that's like the classical old school Xeus. And then we implemented a new server which is compatible with Wasm. So, and we call this JupyterLite. And instead of sending the things via 0MQ, we are compiling the things with mscripten. This spits out a Wasm file and a JavaScript file. And essentially the communication instead of 0MQ is then just plain JavaScript function calls. Okay, so now how do we use these kernels with JupyterLite? So again, we have a Xeus kernel, and we throw the mscripten compiler at it, and it spits out WebAssembly, essentially. Now, we want to use this WebAssembly from JavaScript. So what we do is the first thing we do is we put this in a web worker. Why? Well, if we would use this in a main thread, then the GUI would hang all the time if we execute code, and that would not be a very pleasing experience. So next, the compiled Wasm talks to message passing with a component living in the main thread. It's called we call the iKernel or the kernel interface, and this is TypeScript code. So this kernel then ultimately talks with JupyterLite with just plain function calls. And this is all happening in the GUI thread. So in that way, the GUI is not blocking, and all the heavy lifting is done in the web worker. So web worker are essentially like kind of threads. Okay, so there are many examples of, or a few examples of kernels which we already compiled to WebAssembly. So Python, obviously, Xeus Python works in the browser, as you have heard now. And we also compiled Lua to the browser because, well, Lua is super easy to compile and was kind of a no-brainer. Also SQLite and a few more esoteric languages. Probably no one knows Nelson, but this is like an open source implementation which attempts to implement the MATLAB language. And this also now works in the browser. Okay, so what are the applications? So as I said, this runs in the browser. This means you can embed the Jupyter kernels or JupyterLite kernels directly in your web page. So with these 5, 6 lines, once you add them to your web page, you will have a REPL, and as you see, we specified the kernel to be Lua. So, and this gives you something like this. So this is like just a REPL, not a full-fledged Jupyter lab. And here we can use Lua. So let's see if I'm still able to code Lua. Lua, we start with 1, right? Oops. Okay, and this does what it should do. Lua is in particular nice because Lua compiled to WebAssembly is really tiny compared to Python, so it's just a few megabytes. This is why I like to use it for demos, because it loads right away. But you can also have a full-fledged JupyterLite, and essentially you just use lab here. And this gives you, again, the thing we already saw before. So, how can you deploy Zeus or Zeus Python in that case? So this was already showed in a few talks, but here is a tiny GIF what you can do. So we have a template repository, and you can create your own repository from the template, as we see here in this GIF. And once the repository is cloned, you just need to go to the pages settings and enable that GitHub will deploy it from the GitHub Actions workflow. And that's it. So now it will take maybe 5 minutes to build it, and then you have an URL which gives you a JupyterLite instance, which you can then embed via iframes and use it. Okay, so what's the outlook? What are we going to do next? So we want to improve the XUSLite kernels. So at the moment, it's not possible to dynamically load packages from the Zeus kernels. So once the kernel is started, you cannot add new packages via runtime. But we're working on this by compiling Mamba, our favorite package manager, also to WebAssembly. And then we can just use Mamba from while running the kernel itself. Also, it would be nice if you could load pip packages dynamically. And we know this should work because other kernels, Pyodite for instance, have already done this. Then we would like to see more XUSLite kernels. In particular, what would be really awesome, there is one kernel, XUSCPP, which is in itself quite nice because you can compile, you can use C++ in an interactive fashion without compiling it all the time from the scratch. So it feels like using Python in an interactive way, but it's C++. And that would be quite nice if we could compile this to WebAssembly. This is a bit more complicated because you have then to compile a compiler to WebAssembly. And yeah, and probably the size of the binaries will be pretty large. But nevertheless, it would be awesome to have this. And then we also want to work on a better R kernel for the biologists who still use R. And we want to improve the testing for XUSLite kernels because at the moment it's, well, not that well tested. So we compile the extensions, then we cross the fingers and just hope that it works. Sometimes it does it, sometimes not. Yeah. And so, so we have, so at the moment, for each kernel, you have one repository implementing the C++ code, like Zeus Python. But then we have, unfortunately, for each repo, a tiny bit of JavaScript or TypeScript glue code, which is repetitive work for each and every kernel. And we believe that we can remove this. So in the future, you just will need the C++ implementation, and the glue code will be automatically generated. Okay. So if you want to know more about Jupyter, now here are a few links. And this presentation, you can find it in my GitHub handle. Yeah, and that's it already. And since I have a bit more time, here's a bit of cat content for you. Yeah. And I'm happy to take questions.
Thank you for fabulous work. So I'm curious about the browser side. This seems to be browser agnostic. Any browser that supports WebAssembly will support all of this. Is there an opportunity to optimize, maybe by building a thin browser designed to support WebAssembly? Is there any work on that side?
So the question was if we can implement like a slim browser which is more optimized for WebAssembly. I don't know. I don't implement browsers. Probably. But it's not terribly slow. So you should keep in mind WebAssembly is typically not used for heavy production loads when you want to process gigabytes of data. I think the most important use case is educational use cases, right? Because you don't have to worry about installing Python on the machines. For instance, if you're teaching and you have a class with 20 people, usually there's one computer where it's painful to install Python for obscure reasons and so on. So you usually waste 1 hour of your tutorials just by installing the stack to people, and there they can just go on a website and it works. Or if I want to show my parents what I do for a living, I can just go to their messy computer and start an URL, which is preferable.
Hi, thanks for the really nice talk. I actually have 2 questions. My first question is, can I use JupyterCons with the Zeus Lite Python implementation?
You want to go for the second question also? Or?
Sure, sure. And the second question is, like, let's suppose I have a wrapper kernel around the IPy kernel, and I would like to rewrite it to be, underneath Zeus, so I can use it as like a Zeus Lite kernel. Is there like a clear pathway to that? Like, is it a difficult implementation?
Okay, so the first question is if there are, if it's possible to use comms from Zeus, and the answer is yes. So we even have a widget library directly available in C++. It's called Xwidgets. So this means you can directly include this Xwidget library in the interpreter you're writing in Zeus, and essentially you get the widgets then for free. So this works, yes. And the second question was, you have a wrapper kernel. So wrapper kernel is written in Python, and you implement the methods in Python. How difficult is it to make this happen in Zeus? So it depends a bit if your language has C. What's mandatory? Your language must have C or C++ bindings. So I don't know, if you want to write a Java kernel, well, maybe Zeus is not the right idea for doing this. But if you have a language which is easy to embed in C++, then it's super easy. So essentially you have to implement one method is usually the critical one, the execute code. So you get a bit of string with the code, and then you just need to implement that part which interprets that bit of code. So for instance, the Lua kernel is maybe not even 100 lines of code, so the interesting part. So it should be easy.
We have time for 1 or 2 more questions.
All right. Thank you for this really amazing presentation. So suppose I do have like a Jupyter app installation, and I want to be able to use both the regular Python kernels and like the Zeus Python kernel and just like exchange them easily. Is there a way to do that, or what additional work would need to be done to actually support something like that?
So the question is, you have a Jupyter Hub deployment or installation, and how easy it is to use a regular vanilla Python kernel and the Zeus Python kernels, or what the difference are. There shouldn't be any. So usually the code which runs in your favorite Python kernel will also run in Zeus kernels. But in Zeus Lite, there are some limitations which are intrinsic to WebAssembly. So since it's a sandboxed environment, you cannot do anything, right? So for instance, using threads does not work so good, then stuff with sockets does not work that good. Anything which needs a TCP connection does not work that well. Yeah, but that's just a fact of life. But besides that, there should not be a big difference between the Zeus kernels itself and vanilla Python kernels.
I think my question is more sort of like influenced by the fact that we're not using 0MQ for this implementation. So would there need to be sort of like a rep or something that gets that through?
I'm not sure if I understood the question correctly. So the fact that we are not using 0MQ is not visible to the user. So if you would start a JupyterLite kernel, then you would not notice that it's not using 0MQ.
Okay, we can do one more question up there.
Thanks a lot for the presentation. The ability to run JupyterLite in the browser without any server is extremely nice. But among the applications of WebAssembly, you also have people that are interested in the safety model of WebAssembly or the portability of the corresponding modules, and not only on the browser target. Do you have any use case for the use of such kernels with WebAssembly, but not in the browser?
So I am summarizing the question: can we use these kernels, the WebAssembly kernels, outside of the browser? At the moment, no, but there is kind of a movement where people start to use WebAssembly outside of the browser, just because of the things you mentioned, the strong security guarantees. So there was a quote from the guys who implemented Docker, and they said if WebAssembly would have been there before they implement Docker, they would not have implemented Docker. I'm not sure if I agree 100% with that, because you have limitations with WebAssembly, and it won't execute your code faster than the native kernel would be. Yeah.
All right, thank you very much. If there are any more questions, please ask them to the speakers directly. And thank you.